Welcome back. We're at video 12D. Going to look at some problems with the normal model. So in your notes, the first example, a company that manufactures rivets believes the shear strength in pounds is well modeled by a normal model with a mean strength of 800 pounds and a standard deviation of 50 pounds. We're building a bridge. The bridge requires thousands of these rivets. Would it be safe to use these rivets in a situation that requires shear strength of 750 pounds? And explain. So as soon as you see that you have a normal model, I'd recommend you draw a picture. So draw the normal model. Here is the strength of these rivets in pounds. The average strength is 800. And let's think about what we want. We are in a situation where we're requiring 750 pounds of strength. If we put 750 here, we need the rivets to have that amount of strength, or they can be stronger than that would be okay, but we don't want rivets that where the strength in pounds is under 750. 750, since the standard deviation is 1, this is the mean. This is the mean minus 1 standard deviation. If you think about that then, remember 68% of the observations fell within 1 standard deviation. That left like 16% of the values are down here, below 1 standard deviation of the mean. If we get one of these rivets here, it's not strong enough. So if we get one of these are unsafe. The other 84%, from 1 standard deviation above, these are all okay, these are safe. So you have to ask yourself, you're in charge of construction of this bridge, would you go ahead and use rivets from this company, knowing full well that 16% of them, 16 of them out of every 100 that you go to use are not strong enough. And so hopefully common sense would tell you, wow, that's way too risky, 16%, that's much too high of a likelihood of occurring, so we would choose to not use these rivets. Too many of them are going to be unsafe. Not for something like a bridge, or if they're unsafe, that could have some serious consequences here. Okay, let's look at the second problem. We have a competing supplier of rivets. They're claiming that their rivets also follow a normal distribution, but the average strength is 795, the standard deviation is 15. Now you might look at that and go, well, wait a minute, the average strength of the first company was 800, their average strength is even less. I'm not so sure that this is looking very good. But remember that standard deviation is extremely important, so draw yourself a new picture. This time, last one, the standard deviation was 50. Those rivets were rather inconsistent. This time the standard deviation is 15, so the strength of those rivets is going to be much more consistent. So let's see what this looks like. Again, they follow a normal model. This time they're centered at 795. If we go down 1 standard deviation, if you go down 15, we're at a strength of 780. If we go down a second standard deviation, subtract off another 15, we're at 765. Go down 1 more standard deviation, subtract another 15. Now we're at 750. Remember, we're requiring a shear strength of 750 pounds in this problem. There are still some rivets that are going to be unsafe. They're the ones where the strength is under 750, so these are the unsafe rivets. But hopefully you can see from this picture, compared to the previous problem, there's a lot fewer of them with this company. And so what percentage of them are unsafe? This is the mean. This is 1 standard deviation below. This is 2 standard deviations below. This is 3 standard deviations below the mean. Remember, there are only 0.15% of values that are going to fall down here. And so it would be very rare to get a rivet that would not have the strength that we need. So certainly if you're deciding between these two companies for who you're going to choose your rivets from, we would definitely go with this company, even though the average strength was a little bit smaller. Because of that smaller standard deviation, we have a much smaller likelihood of getting a rivet that's unsafe. And so if 0.15% of them are unsafe, if you look at the area then above, all of these are safe. 100 minus that, 99.85% of the rivets would be safe. If we take 100 minus the ones that are unsafe, so these would be okay to use. New problem. This time we're going to look at corks. So we have a winemaker, has 2 cork cutting machines at a winery. And we're interested in the diameter of the corks. So we have a machine A, cuts corks with a diameter that follows a normal distribution. The average diameter is 3 centimeters. The standard deviation is 0.1. There's machine B. The average diameter of those corks is 3.04 centimeters, and the standard deviation is 0.02 centimeters. Okay, so a couple of questions with this one. Corks with diameters between 2.9 and 3.1 centimeters fit properly in a wine bottle. Obviously, if the diameter is too small, the cork's going to pop right through and end up in the wine. If the diameter is too large, you're not going to be able to stick it in the bottle. So what percentage of corks made by machine A will fit properly? And what are the z-scores that go with these dimensions? Okay, so we're going to focus on machine A for this one. This was machine A. Again, as soon as you see in a problem that you're dealing with the normal model, draw a nice normal model, draw that bell curve. So here are diameters of wine corks. Again. For machine A, the average diameter is 3. We want the corks to be between 2.9 and 3.1 centimeters. So if we go over to 2.9 and 3.1 centimeters, we would like the corks to be within that range. And if you look at model A, a standard deviation is 0.1. So 3.1 is 1 standard deviation above the mean. 2.9 is 1 standard deviation below the mean. 68% of these corks will have the proper diameter here. That's just 1 standard deviation from the mean. So what percentage of corks will fit properly? 68%. Second question there, what z-scores go with those dimensions? Well, if this cork is 1 standard deviation above the mean, it has a z-score of 1. And if this cork is 1 standard deviation below the mean, it has a z-score of -1. So the z-scores that go with those dimensions are -1 and +1. Okay, part B. Now we're going to look at machine B. So what percentage of corks manufactured by machine B will fit properly? And then which machine should be used and which machine should we probably sell on Craigslist? All right, so let's look at machine B. Machine B was here. It had a mean of 3.04. And again, we want to be between 2.9 and 3.1 centimeters. So we want to know what percentage are going to fit properly or within this range. Let's look where 3.1 is. This time the standard deviation is only 0.02. Make that a little bit closer to the middle. If we go up 1 standard deviation, we're at 3.06. If we go up another standard deviation, we're at 3.08. And if we go up another standard deviation, we're at 3.10. So we're going to fit properly here. How about in the other direction? To get to 2.9, if you subtract the standard deviation, we're at 3.02. Subtract another standard deviation, we're at 3. Subtract another standard deviation, you're at 2.98. Then 2.96. We've now gone down 1, 2, 3, 4. I'm still not going to get there with 5. 2.9 is quite a few standard deviations below the mean. If we continued this, it would be 7 standard deviations below the mean. 1, 2, 3, 4, 5, 6, 7. If you continued this, you'd eventually get there. And this is going to continue to taper off here. So all of these are good. The quarks between here and all the way down there are good. You can imagine if below 3 standard deviations, if it's rare to get that kind of quark, it's exceedingly rare to get a quark that would be below 2.9 standard deviations. It would be practically 0. And so if we say that that's practically 0, it probably has a really small chance of occurring. And if we sum up all these probabilities, this one was 3 standard deviations above, which meant that 0.15% will be too big. But pretty much the rest of them are going to be okay. And so again, if you take 100 minus 0.15, we'll find out that 99.85%, roughly, it might be slightly smaller than that, but roughly 99.85% of the quarks will be good. Okay, so if we compare this to our answer in A with machine A, 68% of the quarks were good. With machine B, almost all of them are good, 99.85%. So clearly, machine A is the machine that you should sell on Craigslist. So sell on Craigslist, that machine A. It wasn't bad, but certainly machine B is much, much better than machine A. All right, one last part to this video. Going to sort of give you a preview of what's to come in the next video. Okay, what if we go back to that machine A, we needed to know the percentage of quarks from machine A that have diameters between 2.95 and 3.05. Remember, machine A, the mean was 3. If we went up 1 standard deviation, we were at 3.1. If we went up 2, we'd be at 3.2. Look at 2.95 to 3.05. We cannot use the empirical rule for this. 2.95, that's not 1 standard deviation from the mean. That's probably like a half a standard deviation. 3.05, that's not a nice 1, 2, or 3 standard deviations from the mean. So when boundaries don't fall exactly 1, 2, or 3 standard deviations from the mean, we're going to use StatCrunch to figure that out. We certainly still can. You could get a reasonable guess here as to what that's going to be. You know that if it's 68% fall here, it's going to be a percentage that's smaller than 68%. I'm not sure quite what it is off the top of my head here, but we don't know that exact percentage, so we'll be using StatCrunch for that. And in the real world, this empirical rule is nice and good for start you off on your understanding of the normal model, but most things are not 1, 2, or 3 standard deviations from the mean, so for most of the problems going forward, we're going to go ahead and use StatCrunch. So that's it for this video. You can look forward to that in video 12E.